Now that we've described the benefits of combining object-oriented and functional programming, it's time to address the elephant in the room, namely understanding the role of mutable state in modern Java programs. In part 1 of this lesson, we'll first discuss the pros and cons of so-called pure functions, and we'll then explain why and when to use mutable state in modern Java programs. We'll start our discussion by answering the question, are pure functions really essential for modern Java? As we've discussed in previous lessons, pure functional programming languages disallow and/or strongly discourage side effects and changes to shared state. A function is considered pure if it associates each possible input value with an output value and does nothing else. For example, this Haskell program uses a pure function to compute the nth factorial, which is the product of all positive integers less than or equal to n. Pure functions may simplify programming by making it easier to read, reason about, optimize, test, and maintain software-reliant systems. Of course, easy is relative and is based on various factors. One factor is the experience of programmers. If programmers are well-versed in the patterns and best practices of functional programming, they should find it easy to apply pure functions to simplify their programming tasks. As with any other skill, however, there's a learning curve associated with mastering the use of pure functions. Program requirements are another factor that determines whether or not the use of pure functions is easy. In particular, programs with stateless computations are typically well supported by using pure functions. However, programs that require stateful computations are typically less well supported, since they need to maintain the history of stateful computations over time. Therefore, whether pure functions really make programming easier depends on context. Sometimes pure functions make programming easier, whereas other times pure functions don't make programming easier. However, based on all the hype of functional programming and pure functions, it might be tempting to think that there's no place for mutable state in modern Java and that pure functions are the best and only solution to slay the dragons of complexity. But the key point I want to get across here is there's more to the story, as we'll soon see. To better understand why pure functions aren't the panacea they may appear at first glance, we're going to explore why and when to use mutable state in modern Java. Java is a hybrid programming language, so changes to shared state are allowed. In fact, they're often even encouraged and are required. For example, many Java Collections framework classes, such as ArrayList, Linked List, TreeSet, HashMap, and so on, support mutable shared state for reasons that generalize elsewhere, to other frameworks, to other classes, to other applications. Most of these collections predate modern Java. In the early days of Java, there was much less focus on declarative pure functions and more focus on imperative object-oriented programming. Moreover, the use of mutable objects can often help to optimize performance. This simple example demonstrates some of the performance overhead that's often associated with using immutable objects. The Java code shown in red starts by assigning the string literal A to string S. It then concatenates the string literal B to string S, creating a new instance of S. Next, it takes that instance of S and creates a new string T, and then finally it concatenates the string literal C to T and reassigns that to T. Combining all these immutable Java string objects thus makes copies, which can actually incur significant performance overhead in programs that don't have such trivial strings. However, this code has no side effects. In particular, since strings S and T are distinct immutable objects, reassigning one has no impact or effect on the other. Let's now turn our attention to the Java code in red at the bottom of the slide. This example demonstrates the use of String Builder, which is a mutable Java class that can be used to efficiently concatenate together Java strings and string literals. We start by creating a new string builder that encapsulates the string literal A and assign it to the variable SB. We then append string literal B to the end of SB. Next, we create a new string builder TB that's assigned the value of SB, and finally we append the string literal C to the TB instance of string builder. One of the key benefits of using the mutable string builder class instead of using the immutable string class is that string builder objects largely avoid copying, so they typically are more efficient, especially when you have large strings to concatenate. However, the downside with string builder is since it's mutable, it does allow side effects. In particular, the string builder SB and TB objects reference the same state, so changes to one, such as appending C, will also affect the other. Yet another reason that Java Collection framework classes, as well as other applications and frameworks and classes for that matter, support mutable shared state is that it enables separate tasks to efficiently interact and/or communicate by sharing the mutable state. For example, multiple threads can interact via a shared memoizer cache to optimize performance in a concurrent program. As we'll discuss in more detail in the next part of this lesson, memoization is an optimization technique used primarily to speed up computer programs by storing the results of expensive function calls and returning the cached results when the same inputs occur again. We'll explore the use of a memoizer cache in more detail in the context of an upcoming case study, which can be found in the EX3 project, in my FP folder, in my Modern Java GitHub repository. This case study is a variant of the one we looked at earlier in case study EX1. The EX3 case study composes a pipeline of functions that generate and check smax count positive odd random numbers in parallel and then print which are prime and which aren't. And we'll see that the ability to efficiently interact by using shared mutable state is crucial to the performance and correctness of this program. So that's the end of part 1 of our lesson that describes the role of mutable state in modern Java programs.